Hello, everyone. My name is Acclaim Moila. I'm the application and technical support manager for our genomic services and PacBio applications at Acclaim Biotech. So basically, the aim of today's presentation it's just to kind of just to update everyone on as to how far we are with the work that we're doing with the Africa BioGenome Project group. Since we are doing the hi-fi sequencing. So I'm just gonna highlight a few things that I'm gonna talk throughout the presentation. And obviously, as I've mentioned, our role as in our biotech within this kind of group, our workings with AfricaBP group. And also just to touch on as we celebrate our 20th anniversary this year and the sponsorship that we will be sponsoring towards the AfricaBP for them to sequence up to 10 genomes of non-human African species. And some of the challenges regarding the samples that we receive to do hi-fi sequencing, I think it's a very important aspect that we need to, or needs to be taken into consideration when sending samples for hi-fi sequencing. And we dive into the sequences that we have generated so far. And obviously, just to kind of give it snippets on what the hi-fi reads are and how we generate those hi-fi. And lastly, just to give you an overview of what you can really achieve in terms of data generation from a single SMRT Cell data. Right. Obviously, as a sequencing facility and our involvement with AfricaBP, our aim basically is just our role, let me put it that way, is basically to prepare the samples, library preps, and generate those hi-fi data from every sample that we generate. And then for the samples that are successfully sequenced on PacBio, obviously it would depend on the sample handling, if the sample is really adequate to go into the Hi-C or Omni-C workflow. So in this case, we want to also kind of establish those workflows or set up the workflows so that we can pretty much handle everything from one facility, and that kind of accelerate the work. So we are looking to set up those work protocols. And also, we do participate in the AfricaBP community workshops. So kind of we kind of give insight as to the type of work that we do, some of the critical steps that people need to take into consideration when looking to do long-read sequencing. So we do participate in those educational workshops. And also, obviously, to make it easy for AfricaBP, or much more affordable, but for AfricaBP, we also involve PacBio, which is our partner here in Sub-Saharan Africa, in terms of the consumables as well as reagent discounts that they can provide us, and we pass those discounts down to AfricaBP. And then we are equipping our West Africa and East Africa subsidiaries so that we can be able to kind of give us regional support to AfricaBP members in those areas. And furthermore, we are setting up the SQL systems across East and West Africa so that samples coming from those areas can actually be sequenced in those regions without having to be sent to down to South Africa. As I've mentioned, this year, actually in August, we're celebrating our 20th anniversary. So we started in August of 2002 from just having like 5 employees. So we now have over 150 employees across sub-Saharan areas. We have established offices in Nigeria, Ghana, Tanzania, Kenya, Uganda, and many more other areas. We're looking to have offices, registered offices. Some we still have like a representation in those areas. So our aim basically is just to increase our footprint in Sub-Saharan Africa with registered offices, and those that obviously allows for ease of import-export. Of course, our main office headquarters is based in Pretoria, in Macleneck, where most of the sequencing is done. And then this is basically our presence in Africa. As I've mentioned, our main offices are in Nigeria, Ghana, Tanzania, Uganda, and Kenya. In other areas, we just have representation, but we're looking to have registered offices there. As we celebrate this milestone of 20 years of existence as in our biotech, in the previous year, we had our inaugural Genome Challenge, where we kind of sponsored participant had to kind of submit motivation as to why their selected genomes should be sequenced. And those was done through our YouTube channel. People submitted their applications, and then the public voted on those applications, and the participant with most application votes or likes kind of won the free sequencing. So this year we're pretty much dedicating the entire genome challenge to the AfricaBP community. We will be sponsoring 10 non-human African species. So that would be 2 SMART cells per genome, so a total of 20 SMART cells. And this is to the value of 1.6 million rands, or roughly $95,000 US. So it's a significant contribution from our side. We're very, very proud to do this, and we are very much proud to be associated with AfricaBP and be able to play this crucial role. So there will be announcements, an official announcement from the 1st of September, and then information can be found on how people can participate from AfricaBP website, as well as us in our biotech website. So basically, this is the flyer that you will find. If you go to our website, so you will, from the 1st of September, you will be able to get all the information as to how to apply. Like I said, this is basically out there to the AfricaBP community. There will be a set of selected criteria, of which the AfricaBP chairs will kind of gauge all the application according to those set criteria. So you'll find all the information on our website or the AfricaBP website. Yeah, another important part basically is just to address the challenges that we kind of came across when sequencing these samples. Obviously, some of the samples are kind of archived samples from museum, as we have seen, and those obviously going to bring challenges in terms of having to extract high molecular weights. Sometimes it's impossible, and obviously those samples makes it very difficult to go into the OmniC or Hi-C library prep, as you need really kind of well-preserved or fresh sample. Some of the things that we can do basically is just especially on the collection side, just to go with the dry ice, as liquid nitrogen is going to be highly impossible in most cases. The dry ice works best, as we have seen. So on collection date, you can go with the dry ice, collect the sample, immediately put it in dry ice, transport it. If it does not come straight to our facility on the same day, then you can store that very sample at -8 until it arrives in our biotech offices. It's very, very important to keep that chain of storage to kind of give you the high chance of obtaining really high quality data, as well as doing the Hi-C library prep. So it's a very simple kind of procedure that we need to follow, but if wherever possible, please, if we can get dry ice, that will increase the chance of, especially for Hi-C library prep. And then if you look at some of the samples that we've got, so I have two different profiles here. If you look at the first one this is the actual samples that we sequenced really. If you look at the first one, we have degraded genomic material. I think this was received from Sanbi in Pretoria. Obviously, it's an old sample, and then you can see from the profile there that you didn't really get high molecular weight. It's still sequenceable. We can still sequence that, but it's just that if you have lesser or degraded DNA material, the output then is affected in a way that you have low yield per smart cell. And if you look at the second one, this is the sample from Nguni Gold, where the sample was collected and immediately collected fresh, the blood sample, immediately transported to our offices, and we stored that accordingly at -80. And then if you look at the two profile, you can see the second one that we have a really high molecular weight genomic material, and that translates into the subsequent data generation. And this sample, compared to the other, the degraded DNA, stand a very good chance of generating really good Hi-C or OmniC libraries. So that's a storage. It's very, very critical. The collection and storage of the sample until it gets to the sequencing facility. It's very, very critical in this case. So the genomes that we have sequenced so far. So this we have grouped this into two because some of the species belongs to VGP in the US, and some of the species belongs to the UNISA, the University of South Africa here in South Africa. So we have done 3 genomes for our VGP, big blind snake, the West African mud turtle, and the Goliath heron. So out of those 3, 2 passed or completed sequencing. However, the genomic material was pretty much not ideal, pretty much to the degraded slide that I just showed previously, but we're able to generate enough data to roughly 30 times coverage as required. However, the West African mud turtle, in this case, yeah, the genomic material was not good at all, though we gave it a shot to try and generate data. Yeah, I think we sequenced it across 3 smart cells, and at some point we just had to make a decision that sometimes no matter how many times you're going to sequence that sample, because the nature of the material, you're never going to get anything out of it, and then it will be just like a waste of the consumables and reagents. And I think that sample was over 10 years old, being stored from a museum I think in the Eastern Cape, Port Elizabeth. So out of the 3 species that we did for VGP, only 2 were able to complete. But those 2 samples, I must say, they are not in a good position to go for Hi-C or OmniC sequencing. And then coming to UNISA species, we've generated data for 5 species: Nguni cattle, Nguni sheep, Nguni goat, plant sample, the woolly bottle brush, as well as the bush tea. And all of those, according to the initial agreement, is completed. But just going to explain a bit more on those species in the next slide. So as I've mentioned, the African mud turtle failed. That's why I've put that in red. And then the snake, 1.5 gigabase genome, we're able to generate about 45 gigabase of hi-fi data, which equates to roughly 30 times a coverage. So that is really, really good. And then coming to still in the VGP species, Goliath heron, 1.5 as well, able to generate across, I think, across 2 smart cells, generate about roughly 40 times coverage, about 40 gigabase of high data, sorry. And that equates to roughly 26 times coverage. When we did the preliminary assembly, we did get full genome, 1.5 gigabases, but there is you can still go for an extra smart cell, just make sure that we get that 30 times coverage mark. But yeah, so far it looks good. And then we come to the UNISA species, the woolly bottle brush plant, 1 gigabase genome, and we generated across 2 smart cells, roughly 57 gigabases of data, which equates to 57 times coverage. So that is really, really well. Able to cover that genome really, really, really well. And then we sequenced again the bush tea, 3 gigabase genome, produced roughly 31 gigabases of Hi-Fi data, which is roughly 10 times coverage. Nguni cattle, roughly 3.5 gigabases of genome size. Across 2 smart cells, we're able to produce roughly about 61 gigabases of Hi-Fi data. That equates to 17 times coverage. Nguni sheep, 3.2, able to produce roughly 61 gigabases of Hi-Fi data as well, equates to roughly 19 times coverage. And then lastly, the Nguni goat, similar genome size, and we produced across 2 smart cells, 52 gigabases of Hi-Fi, which is roughly 16 times coverage. Now, these 4 species to reach to a coverage of 30 times coverage, at least 2 more smart cells per genome is required. And we have been in discussion with AfricaBP, so we will generate further data. So that would be roughly 8 more smart cells, 2 smart cells per genome, to make sure that we generate 30 times coverage. The initial agreement was roughly 2 smart cells per genome, but since we can the samples or the data will be analyzed de novo, yeah, you need at least 30 times coverage. So we are in the process now of generating extra data to reach that roughly 90 times 90 gigabases of data, at least. Now, you've heard me talking a lot about Hi-Fi reads, but what is the significance of this Hi-Fi reads? How do we generate this Hi-Fi reads? So basically, the Hi-Fi reads, the high fidelity reads in full, are produced using the PEG-based CCS sequencing mode, the circular consensus sequencing mode, on the PEG-bio systems. So we use the PEG-bio SQL2 systems, and this Hi-Fi reads. So it's the CCS mode basically means that you have a fragment size of a given length, 15 to 20 kb long, and the polymerase is able to go up over that molecules multiple times and generating these sub-reads. And at the end of the sequencing, there is a CCS processing where all these sub-reads now are kind of collapsed into generating a single, very high quality Hi-Fi reads. So obvious, and the good thing is with the Hi-Fi reads, as you generate all these sub-reads, obviously it's a polymer, the nature of the polymerase, you're going to get random errors there and there. And that is the nicest part about this, that the errors are random. And when you generate enough passes across the same molecules, over the same molecules, and when you put all those sub-reads together, you are able to flush out all those random errors. And then you end up with a nice, high quality Hi-Fi read. Is 99.9% accuracy. Now, obviously, at the center of the smart sequencing is the smart cell, which contains 8 million very, very tiny walls. We call those walls the zero mode waveguides, or ZMW in short. So each smart cell has about 8 million of those ZMWs. And each smart cell is able to give you roughly 25 to 30 gigabases of Hi-Fi data. And then what you're looking at here is a tray of 4 smart cells. So meaning you can run at least 4 smart cells per run. But the system, the SQL2 system, is able to run 2 trays, which means 8 smart cells at full capacity. Now, the important thing is, what can you do now with a single smart cell, 25 to 30 gigabases of Hi-Fi data? You're able to generate a reference grade assembly of up to 2 gigabases genome from a single smart cell. You can multiplex up to 96 microbial genomes on a single smart cell. And then you can do variant detection of roughly 3 gigabases or less, and be able to pick up 5-MC methylation. You can do the iso-seq sequencing, the RNA-seq, in PEG-bio terms, we call that iso-seq, the isoform sequencing. For instance, of a human genome or roughly 3 gigabase genome, you can run a single full-length transcript sequencing on a single smartphone. For genome annotation, you can run up to 8 samples or tissues on a single smartphone. For amplicon, custom amplicons, you can multiplex up to 1,000 on a single smartphone. You can multiplex up to 384 SARS-CoV-2 genomes on a single smartphone. And for your 16S or ITS, 18S, yeah, you can multiplex 192. Sometimes we go to 200 amplicons per smartphone. Can do metagenome profiling up to 48 sample, and then metagenome assembly of up to 4 metagenome shotgun samples. So there's a lot that one can achieve from a single smartphone, and with hi-fi sequencing from PET biosequencing. So with that, I would like to thank everyone that for your time to listen to the presentation and kind of an update on how far we've come with the AfricaBP in terms of sequencing their species, and of course with the contribution that we have made through our genome challenge in our 20th anniversary, where we are giving 20 smart cells that will enable the AfricaBP to sequence 10 genomes through us for free. I believe this will definitely take kind of drive the sequencing of all the required genomes even further. So thank you for your time.